badly drawn. And then you, I don't know, you have a cat. Cat. Cannon shoots the cat. The cat has been affixed to a spring. All right. And so after the cannonball, let's see here. The cannonball shoots the cat, and after colliding with the cat and you know, depending on how you feel about cats, you can leave the cat alive or dead. It's up to you. But the cannon, the projectile hits the, and I actually don't even really care what the initial velocity of the shell is. What I want to know is if K is, say, 100 newtons per meter, and after the bullet impacts the cat, with mass m equals to, I don't know, 20 kilograms. The spring compresses, let's say, 0.5 meters. All right. Then, how fast was bullet shell, whatever you want to think about it? I mean, if you'd rather think of, instead of thinking of a bullet, you could think of it as like, as a baby. Like you put a baby in a cannon, and then you shot the baby like to the cat. You know, you could do something like that if you wanted. No?
With the bullet?
No, it's like one of those, you've seen these, like, it's a circus baby. Right? You get you shoot the people through the cannon. It's harmless. Right?
How many kids do you have?
I have 5 kids. Yes. So, not enough to try this, but so how fast was the bullet traveling right before it hits the cat? So, in other words, the yet to be pictured but soon to be pictured question is, what's the speed of bullet or baby, whatever you want to call about it? What's VF right before it hits the cat, given that it hits the cat and then the spring compresses 0.5 meters. So, all right, fine, enough. Energy is conserved in this process, yes? Well, Actually, what I should ask the question is, how fast is the cat, to be more careful, I should say, how fast is the cat moving right after the bullet, after the bullet hits the cat and it's become, you know, the cat and the bullet are stuck together. They're stuck together and they start moving. The question is, how fast is that combined system going? Or if we go back to the baby has grabbed the cat. And of course, they're starting to compress the spring with some initial speed. My question is, what's that initial speed? All right. To understand why I'm waffling on my initial statement, you'll have to look at our example of what's called the ballistic pendulum in a week or two. All right. There's something else at play, which is called the conservation of momentum. And I have to pay attention to that. The conservation of momentum says that, in fact, it's not an entirely conservative process. The process of the cat, the process of the baby grabbing onto the cat and holding onto it is actually not a conservative process. This would be an example of an inelastic collision. More on that later. So again, I'm traveling Right after is what I need. After. Right after. There, now it makes sense. So, and it makes sense in the following sense. So we have 1/2, and by the way, the spring is assumed to be massless. I'm just assuming that the spring is essentially massless, or its mass is much smaller than 20 kilograms, okay? So most of the mass is the cat, all right? So we have 1/2 mv squared is equal to what? 1/2 kx squared. So we don't know v, right? We don't know v. Multiply by 2, we've got v. V squared is equal to k over m, x squared. So my k was 100 newtons over meters. My m was 20 kilograms. And what was my x? 0.5, I told you that. And I have more questions for you guys in just a second. So I said that this was the initial energy, and this is the final energy. What are my initial and final events I'm thinking about? My initial event, again, is right after the baby has grabbed onto the cat and is starting to compress the spring. My final event is when the spring is maximally compressed, which is when? What? It's right before the spring starts to move, starts to expand back, right? The maximum compression happens when the spring stops and then starts to go back, right? Right before it starts to go back. So at the maximum compression, the speed is 0. The kinetic energy is 0 at maximum compression, is my point. That's why there's no kinetic energy term over here. In the flip side, this is purely kinetic. So this is the thing where spring is allowing us to convert this kinetic energy to pure spring potential energy, right? Anyway, so we do the math. What do we got? What's that work out to? 100. That's 5. 1.118, huh? Oh, okay. I thought I got 1.25. So I got you. So we got is it 1.25 meters squared per second squared?
1.12.
But then the square root.
Yeah,
1.12. So, you know what? I think it's reasonable. I think that the baby survives, the cat survives. It's not as exciting as you might have hoped for. Wait, no, we want the baby to survive. The cat, though, no, cats are evil. Just to be clear, right? What's the saying? They're just waiting for you to pass on so they can eat you, right? I mean, that's what people say. No? You're cat people? Fine. Well, let us look at the solution for the test. We have a minute or two here. So, I showed Dr. Dinsmore my test, right? And his initial reaction was, it's crazy. No one will solve any of these. I was like, oh, that's no fun. And I'm pleased to say that for the most part, he was wrong. You guys could solve them. Some of you guys could solve them. However, in fact, none of you could solve the last two problems. No, not one. If it was Sodom and Gomorrah in here, you wouldn't want to look back. That's all I'm saying. So, and that's okay. I mean, you know, we're all still learning. And like I said, the last problem was difficult. I don't deny that. I thought somebody might have gotten the next to last problem, though, but that's okay. Let's start back at the beginning. All right. Oh, come on. What did it just do? Erica? Erica? Chelsea? What's that? Chelsea's not here. Ben? Ben B? Ashton B? Brittany? Taylor Bogert? Kennedy? These are in alphabetical order, so be watching for your name. Liam? Kate?